Hey guys, my name is Philip, and I'm going to talk a bit about lateral movement WMI, but first, an obligatory about me slide. Yeah, so I'm a security researcher at a company called CyberReason, and I'm not really good at choosing creative Twitter handles. And also, this is my first actual conference talk, so you could just mentally uncross that third line. Yeah, I'm pretty stressed. Yeah, cool. So let's begin. We're going to give a short introduction to WMI and just speak a bit about the scope of what's lateral movement in this lecture. I'll show a couple of new methods and improved methods of lateral movement using the WMI feature in Windows. And we'll have a couple of slides about how to detect those things. So in recent times, there has been some work in taking lots of cybersecurity methods and putting them into a neat geometric shape, like the cyber kill chain, the threat attack lifecycle, the attack matrix, and my own invention, which is the hexagon of discomfort, where the red color is symbolizing danger, and the frowny face is your general dissatisfaction with getting hacked. And all of those things pretty much have a part called lateral movement. Now, in recent months, the scope of lateral movement was a bit expanded with stuff like the Eternal Blue exploit and its friends. But the scope in this talk is going to be this. So let's say you as an attacker have gained some kind of initial foothold on a machine, either by phishing or by exploiting some kind of application, but you're greedy. One machine is not enough. What you have on this machine is not interesting enough, and you were lucky enough to find some interesting credentials. So you want to use your newfound credentials and run your evil, disgusting code on another machine. So in the scope of this talk, lateral movement is using authenticated remote execution and running your code using stolen credentials. Cool. So the thing about lateral movements as opposed to gaining the initial foothold is that you don't really subvert any kind of application. You're not using a vulnerability to make software act not as it's supposed to act. You're not exploiting some kind of person, a user using phishing, making them do what they don't really want to do. You're actually using a feature that is intended to let you run code remotely. This means those things probably won't get patched because running code remotely is a feature that actual non-evil people need. So the most common lateral movement methods, at least on Windows environments, are remote service creation, mostly with PSExec and its derivatives, remote task scheduling, and what people mostly call the WMI method of lateral movement, which actually uses a class called Win32 process and a method called create. Now, as you can see, we already have a couple of methods that let us run code remotely. And these are not getting patched because they are features. People actually use them for benign reasons. So why do we even need any more stuff like that? So one of my favorite things is catching a threat actor using some kind of really sophisticated, innovative payload with lots of stealthy techniques. And those attackers use PSExec in an environment that doesn't really create any services remotely. So this is extremely conspicuous. And even though you have this really cool payload, you still get caught and probably lose some of your new evasion techniques. Expanding your toolkit of lateral movement methods allows you to shape how you look to the defenders. So you can better get masked by the noise of what actually happens in a network, or be noisy in channels that are not monitored. So because this is a talk about WMI, I'll give a short explanation about what WMI is. So WMI is a Windows feature that basically allows you to gain information or influence a lot of unrelated elements on a machine without resorting to using lots of different unrelated APIs. So if you want to gain information about stuff like processes, but also monitors and sound cards, etc., instead of writing lots of unrelated code, you basically ask WMI for the relevant class. And this whole thing is available remotely. It basically works remotely just as well as it works locally. And this is done via the DCOM protocol, which is based on DCRPC, or WinRAM, which is based on HTTP. So it looks basically like this. I want to know something about the processes running on my machine. I ask WMI, hey, can you enumerate some processes for me? And that's what happens. You can do this via an SQL-like syntax. You have some really nice PowerShell APIs. And you can also use this to call methods on WMI classes. So you have lots of WMI classes representing really unrelated stuff on a machine. Like you have a class enumerating processes, but you also have Win32 protocol binding, which enumerates network adapters. So without WMI, you need to write a lot of unrelated code. And these things pile up. So some of the things I'm going to show need an understanding of WMI that is a bit deeper. So WMI is made out of three main components: the Win management service, WMI providers, and the WMI repository. The Win management service is actually a mediator between clients of the WMI feature as a whole and all of the other components of the model. So when you are using WMI as a client, the only component you're speaking to is the Win management service. It doesn't matter what you ask of WMI, you speak to the service, it knows what to do. If you're asking for an enumeration of the class, it knows how to, which other component can give this to you. If you ask for a method, the same happens. And all other components of WMI interact solely with the WMI service. Another important component is the WMI providers. So while if you use WMI as a client, you basically magically enumerate lots of weird things on a computer, or you can call methods, but somebody needs to have implemented all of those API calls. Something actually runs the code that you didn't write. So the component that does this is WMI providers. Those are actually implemented as COM DLLs, and they communicate with the WMI service and basically process all of your requests. So the WMI service knows which provider needs to process which request, forwards it to the provider, and then that's what the provider does. The last element is the WMI repository. This actually stores the whole WMI model of classes, their relationships and definitions, and also stores a couple of persistent instances of specific classes. So let's get back to WMI lateral movement as it is known now. This is done by the Win32 process class, which represents a single process on a machine. The class has a method called create, and calling the create process simply calls create process on the machine. So what happens behind the scenes is that we, as a WMI client, speak with either a local or remote instance of the Win management service. It checks which provider is responsible for Win32 process. It finds out it's a provider called SIM132 and passes the request to that provider. The provider knows how to create processes. It creates it, returns all of the return codes back to the WMI service, which then gives it to the client. Well, obviously, this is not all, as I have 50 more minutes of talk. And the WMI feature is pretty vast. There are lots of classes, so we must have another way to run code. The first method, the first technique, is actually an evasion technique. The WMI model is an object-oriented model, which means there are classes that are child classes of other classes. And if you, as a defender, are looking for the Win32 process class, we could just have a class that behaves the same, and it's called something else. So how is it done? WMI has a functionality called class derivation. You can also do it remotely. So you could first create a new derived class on a remote machine. So we create a subclass of Win32 process called Win32 not evil at all. We do it remotely via WMI, so without running any new code. The new code inherits all of the methods of the parent, including create. So we can just call create, and that's it. We have a new process on the machine without directly using Win32 process, which is pretty much what we want. So a short demo. I'm going to show class derivation while I'm monitoring the machine using the WMI activity ETW provider. And let's see how it looks. So that's the provider. We need to enable it first. So if you can see, this is some code that creates a new class and then immediately calls create on the new subclass. So we have created a class called create, launched an instance of evil notepad, and as you can see, Win32 not evil at all, create. So yeah, so if you were looking for Win32 process, it seems you can't find it here. So does this mean we have evaded all detections? Event ID 11 shows all the events of client calls to the Win32 to the WMI management service. This means that we have asked WMI to run Win32 not evil at all create. But we still somehow can see Win32 process create. Why is that? So while we have manipulated the WMI model and created a new class, we haven't really introduced any new code into the machine. So WMI isn't magic. This method needs to be implemented somewhere. So if we look at event 12 of the same provider, this event shows you communication between the WMI service and providers. So the WMI service understands that when we're calling not evil at all, this functionality of the create method is implemented in the SIM132 provider, and it is implemented as Win32 process create. So this evasion isn't perfect. Some takeaways. While this evasion doesn't really work that well for calling methods, if you're trying to do some evil by creating new instances of WMI classes without calling methods, you actually only see the name of the new class you've derived. So this evasion technique is better if you don't really have to use methods for what you want to do. Another way to detect such things is by WMI introspection. WMI itself can tell you a lot about what happens in the WMI model. So you can know when an instance of a class is created or when a method is called, et cetera, et cetera. So if you look at something like select everything from instance creation event, where target instance is some class, this looks at all subclasses. This means that if I look for all instances of Win32 process, I also get all instances of children, of subclasses of Win32 process. Another takeaway is that I had an idea to do something a bit stealthier and use the cloning feature of the WMI model. It's a function which allows you to take a WMI class and create an identical class, which is not a child class of the first one. This didn't work, as while we have copied the definitions of the methods, the WMI service doesn't really know where they are implemented. So you try to call the method, and it tells you there's no provider for that. So this didn't really work. Right. So another technique you can do is taking old lateral movement techniques that don't use WMI and sort of forcefully use them through WMI. So just throwing an acronym at a technique doesn't make it better, and you need to you need to evade something by using this via WMI. Now, the best tools that I know for detecting lateral movement are actually network traffic monitors. So if you use WMI to implement known techniques, traffic is going to look a lot different, which means you can evade lots of network monitors, IDSs, etc. So let's move to the first technique of this sort. The Win32 service class represents a single service on a machine. And the class itself basically provides all of the capability of sc.exe. So we can start a service, we can pause it, stop it, create it, and delete it, which is everything we need to move laterally and create a new service on a target machine. And what's even better is that not only Win32 service provides this capability, but it also has but we also have 3 other classes which allow you to create, delete, and run services. So we have Win32 system driver, terminal service, and Win32 base service, which is actually a parent class of Win32 service. So if you were trying to detect the first one and didn't really write your detection correctly, somebody can still create a service using WMI and evade your detection. So let's look at a bit of PCAPs. The sc.exe uses DCRPC as a protocol. You basically connect to a specific interface, and depending on the operation number you supply, you call a function on the remote service. So the DCRPC interface for the service manager has an operation called create service W or start service, etc. And even while you can encrypt this traffic, even while DCRPC supports traffic encryption, it only encrypts function arguments. This means that even when it's encrypted, you can still know somebody has created a new service or somebody has run a service. But if we use the WMI classes, this looks different. All of WMI basically uses the same DCRPC interface, and all WMI method calls use the same operation number. So if you use the maximum level of encryption on DCRPC, the best thing you can discover while looking at this traffic is that somebody called something using WMI, which is really a lot less informative. So another technique like that is using the Win32 scheduled job, which represents tasks created by AT.exe. Now, this isn't as rich an API as service creation. You can only create and delete tasks. And if you want to enumerate tasks, you basically just enumerate instances of the class. But just like AD.exe, you can easily overcome not being able to run new tasks by scheduling a task to run in 1 minute. Sadly, this method won't work on Win8 and after, because this functionality has been deprecated. Just as you cannot use without significant configuration changes, you can't use AD.exe on Win8 and up. The whole underlying functionality has been deprecated. So trying to use this via WMI simply won't work. And the last technique of this kind is new style scheduled tasks. So AD.exe got replaced by schtasks.exe, which uses a different DCRPC interface. And there's a WMI class for new style scheduled task called PS scheduled task. But this is only available for Win8 and up. This means that while you have the new task scheduler on Windows 7, you can't really replace it with WMI. Another fun thing is that the PowerShell commandlets for scheduled task creation actually use this API. So if you've ever moved laterally using those commandlets, you were probably evading IDS and not knowing it. So as you can see, here you can create tasks, run them, delete them, change them, and add new custom actions. All right. So another demo. I'm going to use WMI to create a service on a remote machine and just run an interpreter from an exe that I dropped earlier. So let's see. Here's Wireshark, which works as a substitute for IDS here. It's filtered to see only service creation related packets. So we're going to create a new service using WMI and see what traffic was generated. So if your PSExec or remote service detection was based on network traffic analysis, this is what you're going to see, which is basically nothing. Right. Another technique you can use to move laterally using WMI is Win32 product. This class actually represents applications installed using messy exec. If you open the add or remove programs dialog in Windows, you basically see everything this class represents. Same as with artifacts you can find in the registry. So Win32 product actually has a method called install. It takes an arbitrary MSI of your choice. You can even point it to a network-hosted MSI file and uses it to install a new package. Not only have you installed, but you can achieve similar functionality with the admin method, and I think also with upgrade. Now, even Metasploit is able to take an arbitrary payload and package it into an MSI. So if you have an exe or a DLL-based payload, it should be pretty easy to turn it into an MSI and use it with Win32 product. And also, there have been instances of pretty sophisticated actors using MSI for payload delivery, but they haven't really used it with MSI-specific lateral movement methods, which is a shame. So let's see a quick demo of this. Here I'm just going to use an MSI package interpreter and use the Win32 product class to run it on a target machine. So we now have a system shell, and we have created 0 services, 0 tasks, and didn't use Win32 process at all. So if your detection was based on a specific execution vector, this is pretty much an unknown execution vector. I did try to do some other stuff with this class, and they didn't really work. First of all, MSI exec itself has a really nice parameter called, which is MSI exec/y. This turns MSI exec into sort of a replacement for regsvr and can run an arbitrary DLL. From what I've tried to do, there isn't really a way to replicate this using the product class, which is a bit of a shame. Another idea I had is because I prefer not to use files that I drop on a machine, I tried hijacking uninstallers. For every installed application, there's a registry a registry entry that specifies an uninstaller, and it is a command line, which means that if you hijack an uninstaller and somehow run it, you can basically supply your own command line and try to uninstall some arbitrary, non-interesting application and run your command line instead. So this also does not work with Win32 product because it for some reason just ignores the uninstaller entry and runs MSI exec with a specific GUID, which is a shame. Right. So another way to run your code remotely is by using evil WMI providers. These providers, as I've said, are where class instances and methods are actually implemented. And this means that if you have your own provider, and which is mostly a COM DLL or a COM exe, and you can run it, you're basically running code on the machine. A guy called Alexander Leary showed during the last DerbyCon way to register a WMI provider using only WMI functions, which means you don't need to run any kind of code on the machine first and just communicate with it through the WMI interface. This means that we can install a new provider. Cool. But this method has a couple of drawbacks. First of all, we need to drop a file on the machine because we need to write a new WMI provider, and we don't like files. Even harder for me, you need to write a WMI provider from scratch. And this is a COM DLL, and it needs to be in a very specific shape, and I'm a lazy person, and I really don't want to write COM. I really don't. So what if I could run something as a WMI provider, but it's just a command line, like has no relation to WMI whatsoever, but it will be run as a WMI provider. To do so, what we need is to create our own COM object with a command line of our choosing. We need to register a new provider, and then we somehow need to get the remote machine to load this provider, so we actually have our code running. So let's begin with creating a COM object. COM objects are identified via a class ID, which is a GUID-like identifier. And if we want to use just some kind of command line, we can put it in a subkey of the class ID called local server 32, which is the subkey for out-of-process COM objects. which means they run as exes and you can supply an arbitrary command line argument. So we have created our COM object. Now we need to register a new WMI provider. Now providers are represented by an internal WMI class called _Win32 provider. It's a pretty big class and it has a lot of properties, but as I am not a developer who actually wants to do useful things with WMI, but I'm more like a monkey hitting it until it submits, we have 3 interesting fields, which are the name field, as we need to reference our WMI provider somehow, the class ID field, which references the COM object we would like to run as the WMI provider, and the hosting model field, which tells WMI how should I run this COM object. So do I want it to run as a standalone exe? Do I want to run it as a DLL I load into a lower privileged provider, into a lower privileged host process? Or do I want to run it as a DLL in a process that is run as system? So we could just create an instance of Win32 provider, and that is enough to register an actual new WMI provider. So we could simply name it whatever we want, supply the class ID of whatever COM object we've created, and set the hosting model to something like self-host, which means an out-of-process COM object which is run as the system user. And that's it. That's what you need to register a provider. But you need to also load it. And WMI providers are generally loaded on demand. That means you have some kind of class and it is implemented in a specific provider. And when somebody asks for this class, if the provider isn't loaded, it is. But as you remember, my WMI provider is PowerShell running calc. It doesn't really implement anything WMI. So we need to find some kind of alternative way to load a WMI provider. Thankfully, there's a class called MSFT providers, and this class has a method called load. MSFT providers actually represents WMI providers which are loaded at this moment in the system. So this load method allows you to load WMI provider basically by name. You could also suspend, resume, and unload providers, but that really does not help me with lateral movement. So this technique didn't work at first, but it turns out that was a typo. But my first instinct was to open IDA, so I can tell you a bit about the internals of this thing. Like, I really didn't need to reverse it at all, but I didn't think I did. I made a typo, right? So the load method checks if Win32 provider is registered correctly. It basically checks this against the WMI repository, and if we register it via PowerShell and provide a real hosting model, this is enough to have a provider considered to be registered correctly. And what happens next is a function called createInstance is called. Now, as you see from this one block, it pretty much unconditionally calls co-getClassObject with your supplied class ID. This means the first time somebody actually checks if your provider is a real WMI provider and not just a bunch of gibberish, it's after your code is run. So the WMI service looks at your local server 32 key under the relevant CLS ID, runs your supplied command line as the system user, and then it tries to communicate with it and query some relevant interfaces, relevant COM interfaces, and it obviously fails because this is not a real WMI provider, but this wasn't really what you were trying to achieve. your code is already running, and you really don't care about whether it functions together with WMI itself. A problem I had with this approach is the self-host model, hosting model, which actually is one of the only ways to run WMI provider as an exe. It runs a system and it leaves a really nasty event in the event log. It basically tells you, hey, you've registered a WMI provider that needs to run a system. This could be a security issue. And if we're going for stealth with our new lateral movement methods, an event saying this could be a security issue really doesn't help. So it turns out that for backwards compatibility, we have an additional hosting model called network service host or self-host. This hosting model makes the WMI service first check if there is a DLL version of the provider, and it tries to load it with a lower privileged hosting process. And if and when it fails, then it just loads it as system, whatever. So this doesn't write anything to the event log. And because we control the COM object and how it's registered in the registry, we can just not supply any kind of DLL version of the provider. So it always runs as system and never writes anything to the event log, at least on registry. What does happen is this COM error event, because you're not really running any real DCOM object. And this is also a known artifact of lots of COM hijacking techniques. But I've seen a lot of these happen with just arbitrary benign COM objects, and this is also really non-informative. So if you work really hard, you can bypass this, but nobody's really looking, at least now. So let's see how it looks. I'm going to remotely write a new COM object into the registry using WMI, register a new provider using the same COM object, and then load it with the MSFT provider's load method. So again, we have a system shell, and again, we have not used any variation of previously known lateral movement methods. These were all of the actual lateral movement techniques I've discovered, but I did want to show like the stupidest thing I found you could do with WMI, which is messing with boot configuration. Boot configuration on Windows is stored in what's called the BCD store. Boot configuration D, forgot what the D stands for. Yeah, and it contains data on the boot manager and bootloader, which files are actually registered at the boot manager and bootloader. And manipulating the BCD is mostly done using the BCD edit tool, or if you have any kind of replacement already running on the machine. But it turns out WMI has a class that represents the BCD store. And like every single WMI class, you could use it remotely. So this allows us to switch winload.exe to a file of our choosing to be used as the bootloader for Windows. And this way we can manipulate the Windows loading process. So we basically just need to open an instance of the BCD store class on the target machine, find the corresponding BCD object for winload.exe, and we can simply set it to calc instead of winload, because some of us cannot write bootkits or don't have the time for that, and then make the machine restart and see it load from calc. So if you want to see how it looks, it's basically like this. Victim is red and attacker is blue because I got distracted. So here's the code for replacing WinLoad with calc. And we can also use, first of all, here we run bcdedit, and we see the Windows bootloader is Windows System32 calc.exe. So we can use WMI to restart the machine and see what happens. So if you've ever wondered how Windows looks like when it tries to load from calc, it's this. Not very usable, but I suppose if you really want to, you can use this for some kind of ransomware scheme or something like that. And you could also use the whole BCD object for more useful evil things, but that's like the stupidest thing I could think about. And all right, let's go on to detection. As I've already shown, the WMI activity ETW provider basically tells you everything you want to know about queries, about method calls, class manipulations of the model itself, and the creation of new instances of classes. And this is basically everything you need to know to detect pretty much all of the methods shown here. Also, using WMI introspection, you could basically gain the same information. The main problem with the ETW provider is that it doesn't really show you the arguments to methods, but it's still enough to detect pretty much all known techniques if you know how to read it. So you have basically these two things, and they can detect pretty much every known WMI attack, and possibly most unknown ones if you just supply it with the correct class name. But as people are mostly not looking at those things, using WMI to move laterally, or at least using the methods described here, will probably evade lots of lateral movement detections. This talk was only about WMI classes provided by Microsoft, but they are not the only ones who write WMI code. So there are some classes and providers that other software and hardware developers write, which means some of them could have unintended functionalities. Like I've seen a way to use my laptop's BIOS WMI provider to set a new BIOS password, and then enable the BIOS password, and then restart the machine, making it unusable for quite a while. But you can probably use it for, I don't know, some more practical stuff. And really knowing what WMI providers you have, which classes you could use on your machine, and knowing what happens in the model could really, it will only do you good, because this is not the only evil you can do with WMI. It's a huge, huge system. And, well, that's about it. Any questions?
Thank you, Philip. Are there any questions? None? Then I'd like to ask you all to give a big applause once again for Philip. Thank you very much.